Hi, my name is Ron Olbeter. Some of you know me. Those that don't, I'm an applications engineer from the New Jersey office. And today we'll be talking about milling interpolation, G12.1. This is a very old code. It's not a new feature, but a lot of people, it's a very complex and it's actually easy to use. It takes a complex function and makes it easy. A lot of people get confused on it because they have a tendency to overthink it. We will break it down a little bit. First off, what milling interpolation is. Milling interpolation is the basic function of milling interpolation is to allow the machine to create a flat or a shape in X and Y plane without physically moving in the Y-axis. It creates a virtual Y-axis by moving the X in and out while the C-axis is rotating. Then go a little bit of history on it before I get too heavy in there. Hello?
Yep,
a little bit of history on it. Oh, sorry. A little bit of history on it is the E2 series machines did not have a Y-axis, and this is going back to around 1992. G12.1 allowed the E2 series machine to create shaped parts that would normally require a Y-axis because it did not need to move in the Y-axis plane by utilizing G12.1. Now, milling interpolation was never available on the L3 series of machine, and there's a reason for that. And it was first introduced for the L4 3225 in August of 1997. Before that, those machines did not have it. The reason it didn't work on the L3 is because of what's required to do milling interpolation. You have to have cutter compensation, a C-axis, a live face tool holder, and the mill must be centered to the material. In other words, you can't be off center or your shape will be very badly deformed. Until around December 2004 also, milling interpolation was around 2004, 2005. Still breaking up?
Breaking up. Yep.
Let's see if I can do something about that. Let me find out something. Is it better like this?
Yep, you're good.
Okay, I'm going to do it through my speakers without the headset. Maybe that'll work better. Basically, the L520, in the middle of its run, milling interpolation became non-optional. Around the time of the introduction of the L520 Type 8 is when that happened. But before that, it required purchase, and now it's standard on the machines. The type of holder you need to use when you're going to milling interpolation is important. You need to use a holder that is parallel to the material. Parallel to material. If the tool is perpendicular, what will happen is you will end up causing a scalloping effect on the part being machined. So the part has to be in line with the material, not perpendicular to the material. This is an important thing. If you do, you can do it this way, but you got to do like 1,000 passes back and forth, and it's very it's time consuming, and it's not very effective. The other thing is you can use Woodruff style cutters as long as they're in that parallel configuration to make shapes that are farther back from the face. So if you didn't have a shape here in the beginning and you want to have like an off-center cam in the middle, you can use a Woodruff cutter to get inside there to do that. And this way you don't affect what's in front. So it makes it a little bit more of an option there. This is how cams would be made and so forth. Milling interpolation has parameters. Originally, before the middle of the run of the L520, we had to physically change the parameters for the mill X and the mill C. These parameters controlled where milling interpolation was used. Number 1125, milling axis number, this set the rotation axis for milling interpolation. 1126 chose the axis name. Now this was done on the L520 Type 7s. In the 1126, it creates a hypothetical name for milling. In other words, if 126 is a 0, it equals Y. If it's a 1, it equals C. This is nothing more than a name. When first turning on milling interpolation on older L522, these parameters needed to be set. Press parameter key, base parameter to get there. On page 2 of 3, $1, you would change 25 to a 3, and the mill C to a 0 if you wanted to use a Y. You would have to change it to the mill C to a 1 if you want to use the C. You would make the same changes for $2. I give this for people that have to set up milling interpolation and have never done it before. These are the parameters that would make it so it works properly. In the middle of the L521, at this point, we could now set the parameters in G12.1 by adding D0 equals C. D0 would tell it whether it's a Y or a C. The E equals C will actually set up the correct axis to be used.
Hey, Ron, whoever's got a ringer in the background, please ask them to mute it.
A ringer? We don't have one here, that's the thing. I haven't been able to find that. Maybe I got a lisp.
Oh, it's gone. I think you're fine. Go ahead.
Okay. Sorry about that. It's a little bit tricky doing this with things going on in the office. One note, the usage of the Y and C, which you've been hearing me talk about, has no effect on the program. They both do the same thing. You use what you are more comfortable with. One reason you have a choice, the A20 with the milling interpolation has to use C. It cannot use Y. So if a shop has A20 machines and L machines, they may prefer to use C's because it covers all their machines and they don't have to think about one doing it with Y and the other doing it with C. So it gives you a choice. And the Y and the C are nothing more than a character. They're exactly the same. It's very important to realize that. By programming with C, you are not programming the C axis. You are programming still the Y axis move inside there, which is not happening with the virtual Y. Cutter compensation is also used in the machine, and it's generally used to control the size of the shape. If you have it at 0, you would get all the tool inside there. If you have the diameter tool, it comes to the proper size there, and you can adjust the size plus or minus a couple thousandths to increase or decrease the size of the shape you're creating. But since you're using cutter comp, the rules of cutter comp still apply, and there has to be a lead-in movement in both X and Y to install the radius of the tool. I do recommend, if possible, that the lead-in move be done before you insert the tool in the material. This way you don't get any erroneous cuts. And you can move it into place and then insert the Z into the material and do the cut. If it's possible to do this, it's the best way. Instead of moving these shape insertion or the lead-in movements for the X and Y while it's in material. The X, Y, and Z axis are available, but any Z axis move has to be done along a line. If you combine the Z with an X or a Y, it will create problems. You'll get flats, you'll get weird shapes. It's not meant to be done that way. You cannot have, because it's creating a virtual Y by moving the X and the C, the Z would just confuses it beyond belief. So Z can be used, but it has to be alone on a line. So you move an X and Y, insert the Z. Simple, straightforward as that. Now it's not moving. There we go. Of course, you must enter into G17 because you're working in the G17 plane. Even if you're not using radius, it has to be in there because the way G12.1 is working by generating the y-axis virtually, there are radii involved inside of it and needs to be in G17 to do it properly. So that's a requirement of Milling Interp. Also, you do not program G0 while you're in G12.1. Technically, it's disabled. And all actual moves would be in G1. But I recommend not putting it in at all, because even though it's disabled, just like REM statements, the computer still reads it, it just doesn't act on it, and it can cause a little bit of problems. So if you leave it out entirely, it will not cause you any issues. Codes such as G2, G3, R, C are available for use during milling interpolation. In other words, you can use all G1, G2, and G3 to move. And the R, C work as well. If you're utilizing the C-axis elsewhere in the program, in other words, if let's say you're doing the C-axis and you're moving to do a cross drill in numerous places, you may have to reposition that C-axis before you go into milling interpolation back to 0 to keep the features aligned before going to 12.1. Otherwise, it takes the last C-axis you use and it bases it off of that movement to go on, which can throw off any kind of like phasing to a cross hole or any other feature that's been done. While machining in G12.1, the tool will never descend below the center of the part. Because of G12.1, it doesn't do it. It will always go to the mill. When making a move that would cause it to happen, the entire part will actually rotate and move out. Now, I threw in the line, you do not need to concern yourself with this when coding, as G12 does it for you. When you code it normally, going below center and everything else. It's G12.1 that does this. So you don't have to think about it. This is more of an information when you're watching it run, how it will look strange and not exactly what you program in, because 12.1 adjusts for it. When you program your part, your datum 0 is the center of the bar, technically, not the part. My bad on that. It is the center of the bar. You just need to code the transition points based off that center position. In other words, everything 0, 0 is the middle of the bar. Everything that you're moving outside is based off that being 0, 0. You do not double your X or Y commands as well. They correct position from the center. The shape program is based off the face of the bar. Program is based off the face of the bar. The easiest way to create the code is to create a circle, draw the shape you wish to create, not necessarily in the circle, but with that circle in mind, and center of the circle being 0, 0. And from that 0, you go to the points where it changes directions. You program the part utilizing transition points of the shape. You would be programming in inches per minute feed rates, and G13.1 cancels G12.1. Now that might have been a little bit confusing, but it'll show up in the next few slides, and we'll clear that issue up.
Hey Ron, I got a question.
Yeah.
Does G12.1 work only with G17?
Yes, it works with G16 as well, but that is that's a different story altogether, because that G16 and G17, well, it is more G16 uses G12.1, but in most cases, because it's working off the center of the bar, I would have to say, yeah, it's always in G17. When you're working G16, you use G12.1 in it to work on the outside. It's a little bit of a reverse situation, but it's different than just straight G12.1. That is the C and Z axis. So it just utilizes it. Can be confusing. Does that help? I hope. The coding direction for G2 and G3, the cutter compensation is reversed. All this is. In other words, what you would normally think is clockwise would actually be counterclockwise. So you have to more or less think of it as if you're behind the guide bushing rather than in front. So if you're making a clockwise move on the shape, you actually have to program it in G3. Now, sometimes it's easier to program the way you're used to and then just reverse the G2s to G3s and the G3s and G2s. And the cutter compensation G41 or G42, just reverse it. The example the next few based off of an L520 type 7. This is just a drawing to show you what's going on. Now the drawing is for programming purposes, not the actual moves that G12.1 makes. It just goes in and out. But what you program is the entry direction, and you have the 0, 0 here, which is the center of the part, and the transition points are these changes in direction here. Those are the numbers you want, like it's 125 up, 125 out from 0, 0. The program here is a working program. More or less started up above, turned on the C, activated G12.1, goes into G17, and then starts working G1, G42, the X, and the Y 125. So it's working actually over here. The Y is at 125, it's actually more like up here, to be honest. The Y is at minus 125 and the X is high. Then you move in with Z, insert the material by itself into the material of the tool. You move it to the first point, which is this, 125, X 125, which is plus 125, Y minus 0.125. That is enough distance to install your cutter compensation. You have to have a little bit extra move. Now, it is a little bit overboard, but it will install it. The next move you see here is a Y positive 125. In other words, it goes from here to this point. And that's usually a comma R for 25. It will generate the radius on this corner over here as it's going, and to the next move, which is X minus 125, then Y minus 125, and then X plus 125, and then one more move across the Y. You always need to overlap, or the shape will not complete. The feed rate is 5, whatever. This will go very well for that, and center. But again, this is just a drawing for creation purposes. It is not the physical moves in the machine. If you're trying to see these moves in the machine, you're not going to see them. This is just a video so you can see what that last set of code did. Come on. There it goes. It's moving in and out. And you see the mill is actually not moving at all. Only the subspinner moves back and forth in the X to create those flats. And you can see the radius in the corners of those the square as well. Now, it also can be used, the same codes, to do the chamfering. All you would do is change the G42 value amount for that tool. This doesn't go twice. Let's run it through again. You can change this, for instance, you can rough and finish if you want to with the same tool, just calling a different offset with a different, how would you call it? A different R value. And you can have it rough and finish. Okay. One last time with that, just in case anybody misses. So it goes in, moves, and then it moves out. Like I said, it's not like the drawing, but that's what it makes. Inside, we take into account the radius of the tool, too, so that can be a little bit bigger in the corners inside there. Anyway, that's enough with that picture. You can also make off-center cams. It's the same basic idea. It's just you start the same start, calling gray, you call the G17 plane, you insert the Z, and then you come down. This one's actually doing a rough and a finish. It goes to 209, goes around halfway to minus 111, then comes back to 209, then goes down to 199. It goes down to 101 and back up to the top. And then 1/2 more for the overlap. Now, when you say 199, this is a 0.3 diameter cam. Well, 0.3 is 150, but if you take off that it is 50 thousandths off center, 3, since it'd be 300 minus 50, 250, 100. Where is that? 50 up, higher, 150 to the center, to the top, 50,000 makes it 200. So from the center here to the top here is 200 or 199. It's a little bit smaller than that. So this is just 10,000s bigger, leaving 10,000s for finishing on the finished cut, because it's 150 plus 50 is 200, 150 minus 50, which is 100, which is the bottom.
Hey, Ron, I got a question here.
Yeah.
Since you were using cutter comp, what p-value should I put in my t-data page?
The p-value is an 8, because that is the center of the cutter. The p-values on cutter comp, basically 4 is for front turning. It's more of the shape involved, front turning. 8 is outside contouring. 3 is outside back turning. And 8 is for a mill, because it's all the way around it. So you would use an 8 or actually 0. Both of them work. But I like to use 8. No, I'm sorry, 9. 9 or 0. You would use a P of 0. Don't mind me, I didn't have my sheets in front of me. I didn't think of it. Change gears. It's a 0. I apologize. 8 is contouring. And you could also use a 9 if you wanted to, but if you leave the number at 0, it will work. I'm sorry. I confused myself. Moving on. This is just an example of a drawing of a shape. The outside here is the circle. The shape is cut away like this. How would you go there? You want just the transition points from here. Let me see if I can pull this off. The transition point for this start of this radius is there. There's also here and here. That was me. Accidentally pressed the wrong key. And you have your transition points here where it's going. So you have your cutter out here. And I'm sorry, it's not going to be very round. You move the cutter to this transition point over here. Then you program it just to do the radius going to this transition point here. So you would have the number for this part here. That's a little dot you can't see. It's not what I wanted. Use this. This is the start of the radius. This is the end of the radius. You would just have a radius going one sweep like that to the next point. So you get to the first point and then sweep it to the next point. Then you can go a straight move, even though you're off the part, to the next one and do it again. Then go to the straight one here and then generate this radius to the top, then go across. Now you probably don't have to cross over that, but I would recommend going this way off the part. But just to show you where that would go. And that's how you would generate that shape. Now, if you have a y-axis, most people would just go there and just program in the x, y with the radius. If you don't have that, this is what you would use. For instance, you have the back, and if you have on the back tools, you don't have a y-axis machine, you have a type 8. You would have to do it with this methodology of G12.1. It gets problematic sometimes when you go below center on y-axis machine that doesn't drop far enough on some tools. This is another way around it. Just so you could get an idea of like starting out, going over to the first point. So basically this part has 1, 2, 3, 4, 5, 6 points, and 7 points if you count going off the part over here. And there'll be 7 lines of code to create this part. Let's get all the way for that. Okay. And everything's based off the 0, so you have it jumping up to here, here, and here. Yeah, I'm repeating myself on that, but I can't stress it enough. One thing of note when it comes to radius feed rates, there is a deviation because you're using cutter comp. It's figuring it to the center of the cutter, not to the edge. So if you program a movement on the outside of a part, it will go faster than intended or slower than intended because it's going at the top with the 10, so the cut at the bottom will be slower, just to show you back on here. So when you got the tool up here, your center line's here, it's got a much longer travel like this. So this would actually be slower. On the same token, when you're going on the inside, it's figuring here, it would be going much faster here than your tool would actually be moving because of the radius of the tool itself. This just, I'll read it. When generating arrays on a part, there are things to consider to achieve the feed rate you actually want. The feed rate is based off the center of the tool, not the cutting edge. It does not matter if you're using cutter comp or not. It's still based off the center. In other words, when you say cutter comp, if your cutter comp is at 0, some people will make their cutter comp 0 and calculate it out with the cutter itself. The feed rate and corner radius would be too fast or too slow depending on whether they are ID or OD radius. To get an accurate OD radius in inches per minute feed rate, you would use the formula below that. In other words, do the feed rate you want times the part radius plus tool radius divided by the part radius again. The example at the bottom is for the OD. In other words, if you wanted a feed rate of 10 inches per minute, you would take the OD radius that you're generating, you would add the cutter radius of a 250 millimeter, which is 125. You'd add those together and divide it by 0.05. And then you do it 10 times this number, which will give you 35 inches per minute. And the feed rate at the cutting point will be 10 inches per minute as compared. And if it's on the inside, this would just change to a negative.
Hey, Ron, I was asked of the tool.
What? What of the tool? The feed rate of what it boils, let me go to the previous picture, maybe that'll help. If you have, let's say here, let's give it a 10. If you're doing this little radius outside here and you have a tool like this, going to here like this, the radius generated for this, if you notice, is much longer than the radius at the bottom. Turn that off. The radius here is bigger. Going center of the radius of the tool to the center of the radius of the tool is much longer and bigger than this short little radius being generated here, if you're going to do that. So the feed rate will be based off of this, which if you want this to go at 10, this would have to go at 35 to be able to generate that at the proper feed rate. On the inside, it works the opposite way because the radius for the inside of the cutter is shorter travel than the actual cut. Okay, so I'm assuming that was based off the center of the cutter.
Sorry, the question was, are you comping the diameter or the radius of the tool?
The radius, always the radius. Cutter comp is always based off the radius of the tool, never the diameter. Even though G12.1 is programmed in diameter, cutter comp is still programmed in radius. Okay. This is just something that people might have been familiar with, which is a hexarow. It could be the outside or the inside. The numbers you see are all you need to generate because what it's giving me is 093.2 to this point and 101 to this point, this being 0, 0. You would use these actual numbers. And then you would say, here, this is a counterclockwise move, which is normally G3, but since it's reversed, if you're doing the outside, like let's say the tool is on the outside of this, it would be a G3 move normally, so you would have to program G2, and you would go to the number here from this to here, 30 thousandths, and up 133. You'd use that as the X and the Y, or Y and the X. No, this is the Y. The X and the Y. So you would have that, those numbers, and just keep using them all over. I mean, this is going to be the same 30 there, and you just generate the radius going back and forth like down the outside. Same story as the inside, but you do have to have a cutter that has smaller than 031 radius because you can't generate a radius smaller than the size of the cutter. So if you use an 031, you more or less would go to center and come back out. So the look on the inside would be more like something like that instead of generating a radius on the bottom if you're going to, if you use an 062 cutter. If you use a smaller, you would generate. But that's just to give you a view of it. Now, the A220, excuse me, it's a G12.1 on A220. It's a little bit different, not a lot, but a little bit, in that it uses C, and it can only use C. You cannot use Y in the A220. It is locked to being using the C. As I said, the C and the Y are nothing more than a character. They don't do anything else. It's just whichever you are more comfortable using. G1, G32, same line moving into C. In this one, I use G3s, just so you can see instead of comma Rs. Moved in on Z, it goes to 125, and it's at this corner on the first line. Then the C moved to 100, so around this point right here. Then it goes a G3. If you notice, that is in the drawing like clockwise move, but it's G3 because it's reversed. But it's going to an X.1 here, generating a 25 thousandths radius, going to these two positions. Then it goes down to 100 here. Again, G3 to this point here, generating a 25 thousandths radius, and so forth. But this is an example of it using G3 to go around the outside of this part. And it works pretty much the same as you would see on the Mitsubishi style controls, as the A220 is a FANUC 321i control. And again, don't forget that this is for drawing purposes. It makes it easier if you do that shit. Get a compass, make a circle, and draw your shape inside of it. It extends beyond, not a problem. And it's not the actual movements. FANUC parameters. These are the parameters for the FANUC machine. The 5450 bit 0, if you make it a 1, the x-axis works in diameter. The reason this is important, the C or Y, if you would say it in the Mitsubishi control, axis is always in diameter. And there's no parameter in there to make that C a radius. By altering the value of the x-axis to diameter, they are both the same. So you're not working one in radius and one in diameter. You're working them both in diameter. Using similar axis. Pardon me?
You cut out there. You got static. Could you repeat that, please?
From what point? 5461?
Yes, please.
Okay, the 5461 is the polar axis for interpolation. The 546 is the linear axis for interpolation, in other words, X. Those are standard and never really get changed. I don't know if I broke up when I was talking about the C and the Y x-axis, but the x-axis can be in diameter or radius. The y-axis, the c-axis is always in diameter. By changing the bit to a 1, you make the x diameter. So both work in diameter instead of one being in radius and one being in diameter, which could get very confusing. $2 has the same parameters, except 5461 is set to a 4 for the C2 polar axis, where the 5 is on $1 for the C1. And the x-axis, of course, is a 1. That never really changes.
I got a question here for you, Ron.
Sure.
Can the G12.1 be programmed in diameter and radial values?
No. G12.1 is always in direct distances. In other words, if you're making a 250 square, you would be programming up 125 and down 125. So you would have to say that is diametric. It is not cut in half. So you have, well, here you would be 125 up. This will make a 250 square. It cannot be done any other way inside milling interpolation. Again, remember, this is actually a very old code, but it is very powerful and it's very viable and has not lost its viability at all. It's like a fantastic little function of the machine. But in the design, it's designed to work in diameter. Yeah, diameter plus and minus. So you don't cut it in half. Okay, next. The L720 type 9 and the L20E type 9, milling interpolation. Now, this has changed a little bit in here, depending on where it's used. On the back, it's pretty much the same, but when you work with the rack, because of one of the functions of the rack, of the GSE310, the holder itself can be on a cross where the tool is on a face, and it needs to have mirror image on for it to work in XY properly. And these are the codes for the L720, M130, 132, and the L20E, which is 211, 212. Now I got a little bit more of a drawing here to show that makes sense. This is the tool holder, which uses these modular blocks. The tool holder itself is on cross, but these blocks are on face to work with milling interpolation. Now, that's why with this thing being on cross, it kind of confuses itself with its moves for X and Y, and you need to have milling interpolation mirrored so that it goes correct for when it works on the face of the tool. And basically, it's not that big a deal because all you do is on this thing or insert the lines that are in red. The coding is exactly the same as what you've seen before. It's just in the beginning you turn on the mirror image, and with a G140 to set everything correct, and a G50. Then at the end you go 212, which will turn the mirror image is turned off, and then it turns it on at the end, because mirror image when you're using that block is on. The next code will change all the G140 settings back if needed. You can also use the G141 to set them back. But by inserting these codes, it will work from tool holder 11 through 13. In other words, these holders here. If you got a tool in here with a face tool, you do not need it. If you have it in the back, you do not need it. But on this one, because it is mirror image by working on the side, because it's breaking this block, in other words, here X is up and down. Over here, X is in and out. It's the mirror image of Y and X. And that's why it is necessary, whereas this is going to have to work in the opposite of what it is here. G12.1 with a B-axis. You still have to use, on the B-axis part of it, you still have to use M211 and M212 mirror image code. You can only use G910 B0 because the other ones are functions with like angular movements. You cannot do G12.1 at an angle. So G173 is also not feasible. The C-axis doesn't work on an angle. Whenever we do angular work, we always move the tool around at an angle. You do not move, the C is on the center of the spindle. It does not bend. So it cannot do the milling interpolation on an angular shape like this. And that pretty much covers everything about G12.1.